Okay, in lab this week we're doing a Bradford test or Bradford assay, and that's a test that we use to measure the amount of proteins. And as you're kind of learning in class, proteins are the key functional unit of cells. DNA is transcribed into RNA, RNA is translated into protein. DNA and RNA have some functional role in the cell, but for the most part they just translate information. The key thing is measuring and seeing what proteins do. And the first step to do that is to see how much of them you're actually dealing with. So we're just going to see the raw amounts. This is a Bradford test is the first thing you do before doing Western blot, so you know how much protein to put into the test, and you can then see like a specific protein later. But for the purposes of this day's lab, I'm just going to go through an example with some of my data and show you how on Excel how to do this conversion. There is a way in your book that's also easy enough if you want to just study it that way. I'm going to go through how I do a Bradford assay, and you can use this same technique if you're able to bring like a small computer or tablet that you're comfortable using Excel with. I think it makes it a lot easier. Okay, so what we're looking at here is absorbance data. These are all different data points for sets of protein, and there's triplicate of each set. So these three right here, for example, these are replicate 1, 2, and 3 of a certain set. So let's do this first. This is our raw data, so I'm going to show you guys what this is first. So these are our standards, and this is what we're going to use to make a standard curve so that we can see where on that standard curve our unknown protein is, because we know the concentration that I put in here. So in this case, if I spell something wrong, forgive me. Yeah. In any case, so right now, the concentration of my first standard was just 1 microgram per microliter. The next was 2, 3, 4, then I did 6, and then I did 8 micrograms per microliter. So this is kind of a lot, 8 is. A lot of the times you'll see less than 1, honestly, but this will give us a good curve. So what these concentrations represent are the x-axis of our standard curve. So if I take the average here, oops, no, right there, because these are all the same concentration. These are all 1, but the absorbance can change a little bit. See how it kind of goes around? But the average absorbance is what I'm going to use. So here I'm going to write replicate 1, and I think I can do replicate 2 and 3. So these are all the same concentration, but the absorbance always changes for whatever reason, so it's good to have 3 in this case, and you can have a nice average. In your case in lab, you're getting an average of 2, so that'll be even easier. So using Excel, I can just pull this right down, and now I have averages all the way. So as you can see, the concentration, or as the concentration increases, see if I can just paste text. Just give me the values, yeah. So, as you can see, as concentration increases from 1 to 8, the absorbance increases. And we're measuring this at the 595 wavelength, I believe. So, easy enough right here, we have known concentrations and their respective absorbances. So if we go to Insert, we can just do a simple XY scatter. Computer's a little slow. And see, you kind of have that line right there. So if you right-click this line, help me out here. Add trend line. And I'm on a Mac, like kind of an older one, so this may not be perfect. So we're going to display the equation on the chart. So this is our conversion factor, quote unquote, the slope of this line. So if you see right now, these are our concentrations. See 1, 2, 3, 4, 6, 8. And the computer is able to generate a curve for us and an equation. So this is much easier than figuring out the conversion factor, at least in my mind. So, and you still get the same result, and it's all good. So now we have the standard curve. We know that the relation between increasing concentration has this slope and this b value, y equals mx plus b, when you're considering how the absorbance goes up. And you'll notice the absorbance doesn't change too much, but now we can plot anywhere on this line, like say we had a concentration of 4.5, it would plot right here. and that is the absorbance that we would see in a 4.5 concentration. Okay, so let's see our unknowns. These are 8 different cell samples that I use. So I actually break up human cancer cells. Oh, come on, just come here. So I break up human cancer cells, and I measure them for their lysate, and the lysate is what the proteins are contained in. So this is cell lines, and then this is all just, I'm just doing an example from my data, so I'll do it completely. And then I treat them with a certain amount of drugs. So in this case, DMSO is just a control, IBET1 is a certain inhibitor, and then I do 100 JQ1 and 500 JQ1. And in my first cell line is called RI1. The second cell line is U2932. So like I said, this is my data, so I'm not doing the exact protocol that you guys will use. For example, I have 3 replicates. You'll only have 2, and I think you'll have fewer samples to do. But what this kind of shows is how convenient Excel can be for doing these. Oops, those numbered is supposed to stay the same, but oh boy, all right. Okay, so now we're finally there. All right, so we can do the same thing we did before. We just get the average of our 3 replicates, because this is just the average. This is the average absorbance across 3, so it gives us a good little consensus. So now what we're going to do is we're going to take these averages and, well, actually they can just stay like that. What we need is this equation. I think I can copy it down here. I might be able to. No. So we have the standard curve, and if you do the algebra, we can come up with an equation. I can see if I can write it like this. But we want to isolate the x variable, right? Because that's concentration. We have absorbances here. This is what we absorb. This is what you'll see in the spectrophotometer. But we need that x. So if we isolate, y is going to be, so y is our average because y is our absorbance. Oh, I have to do an equal sign. So if you break this down in algebra, y minus 0.1175, and that's our b, divided by our slope, and then we've isolated x. So we've taken this, minus over to y, and then divide by this factor, 7.3. Oops, no, we don't need that. And there we go. This is shorthand for concentration. Is that little c in brackets. And using the same equation, it'll take our absorbance, our average absorbance, and basically spit out a concentration. So this concentration is in micrograms per microliter. So that's how much protein is in each of these little treatments. So this is, this is cell line 1, 2, 3. You get the idea. So we have 8 different cell lines that we've now calculated. Oh man, I don't know why it's doing this. Do it the old way. We now have, for each of these cell lines, a concentration of protein. And if I wanted to go back and say, because I think you guys will have to, so this is my total lysate. Let's say in each one I had 75 microliters. And we'll show, yeah, here we'll notate that here. And that's just the case the whole way. For each of these tubes, for example, we'd have 75. We would just concentration times the total mils, And this is our total micrograms of protein in each tube. So I got this 75 just because that's what I dissolved the protein in, and that's like kind of that extraction buffer. But you can take that amount and times it by the concentration to get the total amount. But in this case, with this data, I'm ready to do a Western blot and measure protein.